Okay, let's look at how to run a conditional probability question when we're just given percentages. And these types of questions come up often when you're dealing with the scenario of some sort of virus or illness or condition that is detected by a test. And then that test has a certain accuracy percentage. And when you're given that kind of information, kind of little bells and whistles can go off and go, oh, yeah, this is going to be that technique where we're going to create a fictitious large sample of people. And then we're going to project the percentages that are given in the context of the question onto that group of people. And thus we will now have, kind of this fictional set of people that have the condition and don't have the condition and tested positive and didn't test positive, and we can put that all on a nice little table, and then it makes it very easy to answer any of the given condition questions that we might be faced with these types of scenarios. So the first thing we always do when we recognize that, this is the scenario we have, like this says, a certain virus infects 1 in every 400 people, a test used to detect it. If a person is positive 90% of the time, if the person has the virus, and 5% of the time if the person does not have the virus. So it's basically saying that it gives you a true positive 90% of the time, but it gives you a false positive 5% of the time, right? It's used to detect the virus and it is positive 90% of the time if the person has the virus, right? So if they have it, 90% of the time the test says they have it, and 5% of the time if the person does not have it. So it basically says they have it 5% of the time when they don't. And that's why it says this 5% is called a false positive. And then they tell you what A and B are so that you can translate, the symbols down below. But I always say, don't worry about the symbols, just read the English. And if they don't give you the English, then yes, you got to translate the symbols back in English, because you always want to be asking yourself these questions in English. You don't want to be asking, what's the probability of A given B? No, you want to say to yourself, what's the probability that a person has the virus given that they have tested positive? That makes it easier for us to visualize, okay, the given condition is now my new subset. I'm only going to look at those people who had a positive test result. And then within that subset of people, how many of them actually had the virus? That becomes my good. And then the total is just all the people that tested positive. I do good over total. And blam, that's my answer, right? Make it nice and easy on us. We don't have to worry about using all these silly formulas. Okay, but in order to organize our thoughts and get these numbers down so we can figure out what the good is and what the total is, you always want just a simple table. Okay? And the table is going to be a 3 by 3. And the reason why is you're going to have, tested positive, tested negative, right? Has the disease, right, or whatever, and then doesn't have it. And then down here are going to be your totals, right? Over here are going to be your totals. And then, of course, this bottom corner is going to be the grand total of people. Okay, now they tell us 1 in every 400 people has this disease, this virus, sorry, that they're testing for. So 1 in 400. We don't want to deal with only one person having the disease, because then we have to do percentages of one, and that becomes a pain in the butt. So instead, we want a bigger amount of people. We want a bigger sample size than just 400 people. Now, you could probably get away with just 4,010, right? Multiply both numbers by 10. But big numbers are fine. We can do big numbers in our calculators. So just to be safe that we don't run into any decimals, let's say we have 100 people in, and then we just add 2 zeros, right, in 40,000. So that means we're going to have 40,000 total people. So this is our fictitious group of people that are walking into our testing labs to get this test taken to figure out if they have the virus. Well, they say 100 in the 40,000 have it. So that's the 100 that have it. So how many don't? Well, that's just the 40,000 minus the 100. So that's 39,000, right? 900 don't have it. Okay. The next thing they tell us is that a test used to detect the virus is positive 90% of the time if the person has the virus. Okay, so these 100 people walk into the clinic, they take the test, they all have the virus. The test is 90% accurate, so that means it's going to come back and give a positive result 90% of the time for those people. So we take 90% of 100, and that means we have 90 people who had the virus and the test come back and says they have it, and then the other 10, the test actually gave us what's called a false negative because they actually have the virus, but it came back and said they didn't. The next piece of information they tell us is that, and if the person and it tells us 5% of the time, if the person does not have the virus, it comes back as positive. So down here, they don't have the virus. It's going to come back positive 5% of the time. So we need to do 5% of 39,900, right? So you take 39,900, multiply that by 0.05, you're 5%. And that tells us that out of those 39,000 people, we would get 1,995, right? 1995 positive test results. That's our false positives. And then over here, we would get our true negatives the right ways by just taking the 3990 and subtracting that. So subtract that from 39,900. I think I said 3990 by mistake. And that gives us the other 37,905 people. So now we can fill out our other totals. We know now that there was a total of 37,915 people, right? Add these two numbers that received a negative test result. And we add these two together, right? 1995 plus 90 gives us 2085. That's how many people got a positive result. And then, of course, if you add these two numbers together, you'll see it adds back up to 40,000 like it should. So we've basically taken a confusing question that just has all these percentages staring at us. We've applied the information to a fictitious group of people. So now in our mind's eye, we can visualize these 40,000 people walking into a clinic and taking this test, and we would have this data. We would have 90 that come back with a positive result who actually have it. We'd have 1,995 people that come back with a positive result that actually don't have it, and so on and so on and so forth. So now the first question, find the probability that the person has the virus given that they have tested positive. Well, given that they have tested positive means we're only looking at these two groups, i.e. the total of 2,085. So that's my new total. So good over total, right? Good over total is what probability is. Well, we already know the total is the 2,085 total positive test results, because the given condition, right, the B part, I keep circling both, the B part, the given that they have tested positive, that is our new total. And then within that new subset, within that new group, right, instead of looking at everybody, we're only looking at the people who tested positive. So within that subset, how many of them satisfy the A condition of being a person who actually has the virus? Well, that's the 90 here. So we do 90 over 2,085, stick that in our calculator, get a decimal, convert it to a percentage by multiplying by 100, and that's how we get 4.31, blah, 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 blah. Okay? Now the second one says, find the probability that a person does not have the virus given that they test negative. Okay, so now our given condition is, do this one in green, right? Now our given condition is they test negative. So now we're looking at these people. So now we have a new good over total. And our total is the 37,915. And they say, find the probability that the person has the virus given that they have tested, sorry, find, I'm reading the wrong one. Find the probability that a person does not have the virus given that they tested negative. So the does not have the virus are these people. So that's the 37,905. And you can see those things are almost the same number, right? That's why it's so close to 1. When you do the math, you get the 99.97, blah, blah, blah. So what does this mean in the context of the real world? That means if you walk in and you take the test and the test comes back negative, then that's a 99.97% chance that you don't have this virus. However, because the virus infects such a small number of people, right, only 1 in 400, that just because your test result comes back positive and it's 90% accurate doesn't mean there's a 90% chance that you have it. It means there's really only a 4% chance that you have it. And that's why anytime a test comes back positive for something like this, they will run the result again and again and again. Because every time you run it again, if you get that same result, you're increasing the percentage that they actually have it by magnitudes. It goes up very quickly. Like if you test 3 times, you get up to an accuracy level close to that 90%. So you can be much more confident in saying, yeah, sorry, you have this virus, right? And then, of course, viruses that are more virulent than this, where, more people get it than 1 in 400, you don't have to worry about testing multiple times because, the numbers aren't so disproportionate. Okay, let's look at another example so you can see how we can do this again with a table. We recognize this is a table question because we've got a disease. It has an incident rate, right? That's just another way of saying, 1 in 400, if you did 1 divided by 400, that would have given you the incident rate as a percentage. So this is just telling you the percentage of people have it. That's the same thing as it's the same information that they gave us when they said 1 in 400. And then instead of telling us how accurate the test is, they tell us the false negative rate and the false positive rate. Well, we talked about what the false negatives and positives are in our table, so we can just fill in those boxes instead of the other ones, right? So we're still doing the same process. It's just they're giving us a different set of information that we fill in, and then we compute the others, right? You'll remember that in the previous example, we knew the 90 because they told us it was 90% positive or 90% positive rate. And then we calculated 10 by just doing the difference because we knew these two things had to add to 100. And then they told us that, this is how accurate it was for a negative result. And so we got that. And then we went backwards with this one. Or no, that's right. They told us how this number was. And then we added backwards to this one. So it's just a matter of whatever they give us, we know that these two numbers have to add to that total, right? These two have to add to that total. They always add vertically down, right? So it makes it really easy to fill in the blanks. So again, we'll do the same thing with the has and the don'ts, right? Have the disease, don't have the disease, testing positive, testing negative. These are our totals over here. They tell us we have an incident rate of 0.3%, right? 0.3%. Remember, that equals 0.003 as a decimal, okay? So that is our rate of having it. Again, we want to make sure that we have big numbers, right? So we don't want to do like 100 people because if we did that, it would be 0.3 of a person. If we did 1,000 people, we would just have 3 people. So let's do 100,000 again. I know we did 400,000 before, but I'm saying on the same scale. So do 0.03% of 100,000, right? Take 100,000 and multiply it by 0.003, and you get 300. That's a better number because now when we start taking small percentages of that, we're still going to have a whole number of people. Okay, so 100,000, that's our total. Those are the number of people coming into our clinic. We know that, less than 1%, in fact, 0.3%. So we know that 300 have the virus. Then we go, okay, so we subtract that. So that means 99,700 don't have the virus. Now we come back and say, A false negative is 4%. Well, a false negative, remember, is when you get a negative result, but you actually have the virus. So a false negative happens here. So this would happen 4% of the time. So we just have to take 4% of 300, and that gives us 12. And that means that the difference, right, 300 minus 12, the 288 would be, they would get an accurate positive, right? They get a true positive. Okay, and then the next thing it tells us is that the false positive rate is 1%. And the false positive is down here, right? Where a false positive means you get a positive rate when you actually don't have it. And that's the square that represents people who don't have it and have a positive result. And that's 1%. So we take 1% of all the people who walked into the clinic who didn't have it, i.e. the 99,700. We take 1% of that, so 99,700 times 0.01, right? And you get 997. You see why we like these bigger numbers so we don't get any decimals, 997. And then we subtract that, right, from the 99,000 to get the leftover. 99,700 minus that gives us the remaining 98,703. And then we can do the math right in both directions. So 98,703 plus 12 gives us 715. And then add these two together, right? 8 and 7 is 15. Carry the 1 gives us 18. Carry the 1 gives us 10, 12. 1285. Okay, so now we have all of our numbers. Now we can answer anything they want. Compute the probability that a person who tests positive actually has the disease. Now, the wording of this question is a little tricky. What's the given? What are they asking? So they're asking how likely is something true given that we know something else is true. Well, when they say what's the probability that a person who tests positive actually has the disease, they're basically saying what's the probability that the person actually has the disease if we know they tested positive. So you see how the testing positive is the given condition, and in this case, testing positive is the given condition, so we're looking at this subset. And so now we know that for good over total, we have a total of 1285 because those are the ones who tested positive. And since we know, right, we know that a person tested positive, what's the probability that they actually have the disease? See that how the actually is kind of the thing that we're not sure of, right? The person who tests, that's a definite. And then actually is, did it happen? That's the thing we're asking. Is that what happened? Right? That's the A, the thing we're unsure of. And so actually has the disease, right? That's the 288. So 288 over that. And of course you do 288. You divide by 1285. And you get 0.224124, blah, 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 blah. You get that answer. Okay? So that's how we want to tackle these types of questions where they're giving us percentages of incident rates and percentages of a population that have something. And whenever they give us a test accuracy rate, those scenarios are always so much easier to wrap our brains around if instead of dealing with percentages of percentages of percentages and all that ugly decimals flying around, give yourself a big, huge population, something on the magnitude of 100,000 or more, right? So 100,000, 400,000, those kinds of things. And pick a number that keeps things easy to do the math, right? We picked 100,000 because that's really easy to take percentages of. In the previous example, we did 40,000 because that was a nice, easy multiple of this 1 in 400 thing. So those are the ideas that will keep the numbers as whole numbers, and it'll make it easier for us to do the math and not have decimals to worry about. Okay, I hope that helps.